Okay, so the last topic we're going to look at is back to derivatives. We save it for last in this class, not because it's not important, but because it's actually important that you have an understanding of derivatives and antiderivatives before we do this final topic. It's kind of a standalone topic. It's also our last one, so if you are excited about that, trust me, I am just as excited. All right, so we are used to equations that are in terms of one variable. Okay, all semester we've been dealing with things that have one variable. Okay, so an example. We have looked at functions like f of x equals x squared minus 2x plus 3. Okay, or maybe something with another variable like t or u or something like that. But sometimes we need more than one variable in a single problem. Remember, variables are just unknowns. So sometimes in real situations, we might have more than one thing that is unknown, more than one thing that is open to change. So if we truly want to describe more realistic scenarios, more often you're going to have more than one variable. Now we're only going to do 2 variables, but just know that there can be more than one. So instead of f of x, you might see something like f of xy. And then notice the equation has both x's and y's in them. So we're going to learn some notation, but we can take what is called a partial derivative, where you just look at the derivative with respect to one variable or the other. Okay, we're going to do plenty of examples of this, so don't get discouraged. Okay, so we're going to take the partial derivative with respect to one of the variables, and this is the key to the whole thing, while treating the other variables as constants. So we may have 2 unknowns, and we're going to say what would be the rate of change of the first variable if we kept the second one constant. Okay, and then we might also figure the other option out, which is what if we left the first variable constant and we changed the second variable, then what would be the rate of change? Okay, so there's some notation that you need to be aware of. So the first one is, it's kind of like an italics D, but it's like D, Z, sorry, dy. Sorry, let's make this dx. Okay, so it's kind of an italics looking D. Okay, so that means partial derivative with respect to x, or if you see f with a little tiny subscript under it, that would mean the partial derivative with respect to x. Or if you saw f with a little x down here of xy, okay, all these take the derivative of with respect to x. Okay, so it's kind of new notation. So if you have a subscript of x, either with the xy notation or without, or if it says dz dx, okay, whatever's on the bottom, that's telling you kind of what to take the derivative with respect to. So if you have dz dy, or f with a subscript of y, or f with a subscript of y, and then xy. This just says, hey, we're going to use the letters x and y, but we want the derivative with respect to y. Okay, all these mean take the derivative with respect to y. Let's stick the word mean in there. Okay, all these mean take the derivative with respect to x. All these mean take the derivative with respect to y. All right, so we're going to take some pauses here. If you need to, then pause the video as you're thinking about this. But let's start with a pretty simple equation. So f of xy equals 4x minus 3y plus 6. In other words, there's two unknowns. X, we don't know what the value of that is, and we don't know what the value of y is. Okay, so if I ask you to find f sub x of xy, okay, this means take the derivative with respect to x. In other words, this is important. It means treat y as a constant. So treat y as just a regular number. Okay, so when you take the derivative of 4x, you treat that as normal because it's something involving x. But when you take the derivative of 3y, if y is just a constant, then this whole thing is a constant. And what's the derivative of a constant? It is 0. Derivative of 6 is also 0. Keep in mind, we've been discussing antiderivatives for a while, so now you need to switch your mind back to derivatives. Okay, so let's look at the same problem, but the derivative with respect to y. So here, I'm going to treat anything else as a constant. So I'm going to treat x as a constant. Okay, so coming back up here, that means 4x, that means that's a constant. So the derivative of a constant is always 0. The derivative of minus 3y would be done as usual because I'm doing the derivative with respect to y, and then the derivative of this constant is just 0. Okay, so the rate of change, this means that the rate of change, let's go ahead and write this down. So the rate of change for x is 4 when y remains constant. And the rate of change for y is negative 3 when x remains constant. In other words, the x values are increasing, the y values are decreasing because I have a negative slope. All right, so admittedly, this is going to take you some practice. Because we're going back to the world of derivatives when we've been discussing antiderivatives for a time, but also just because you're going to have to train your mind to think, I need to treat whatever variable as a constant, and that can be a little bit of a challenge. So notice the reason z is incorporated is I can't say that y equals something involving y. So instead of y, we use the next letter, which is z. Okay, so notice, and this is wrong, sorry, this should be a z. So dz, dx, that means the derivative of the z equation, but with respect to x. Okay, in other words, I'm telling you to treat y as a constant. Okay, so I want to do dz dx. Okay, so anything with an x term, just an x term, just gets treated like normal. Okay, the derivative of x cubed is still 3x squared. Okay, but then when I get here, I would do the derivative of 4x squared like normal. Okay, but then I would need to treat y as a constant. So my suggestion is for you to pull the constants down. Notice 4 and y are both constants, so I'm going to pull those down. And then do the derivative of x squared as you normally would, so that would be 2x. Careful about this, right? If this whole thing is a constant, the derivative of a constant is just 0. So in the end, we get 3x squared plus 8xy. Okay, and that's as far as you can go with these. You shouldn't be surprised when the derivatives leave x and y because the original equations have x and y. All right, so what about this? Find dz dy if z equals 5x plus 2y to the 10th power. So we're finding the derivative with respect to y, so we're going to treat x as a constant. Okay, so let's see if we can do this and remember what rule we would need to use. So, in other words, I'm going to do power rule. So 10 times 5x plus 2y to the 9th power. Okay, this is just half of chain rule, right? This is the derivative of the outside. And I need chain rule here because I have something more complicated than just a plain variable to the 10th power. Okay, I have parentheses to the 10th power. Okay, so then I also need to multiply by the derivative of the inside, but just be careful. The derivative of the inside is only with respect to y. So the derivative of this constant is just going to be 0. And the derivative of 2y is done as it normally is, so it's just a 2. So this is the derivative of the inside. So in the end, this is just 20 times 5x plus 2y to the 9th power. Okay, so again, I know this is strange, but you just have to train your brain to think, when I'm finding a derivative with respect to a variable, I need to basically treat the other one as if it's just a number. Okay. All right, so we can also find specific values of functions with multiple variables. And their partial derivatives. So we're still going to practice some more partial derivatives. I'm just going to introduce one extra step. All right, so let's say that I had this multivariable problem. F of xy is equal to 5x cubed y minus 4xy squared. So first, let's say I asked you to find f of 1 comma 3. Now notice I didn't give any subscripts, right? So I'm just trying to tell you that this is the x I want you to use and this is the y I want you to use. Okay, so this is just a plug-in problem. So we're going to plug in 1 everywhere there's an x, and we're going to plug in 3 everywhere there's a y. Okay, so if we worked this out, we're going to end up getting 15 on the first thing, right? Because this is 1 times 5 times 3, that's 15. Here I would do exponents first, so 9 times 4 would be 36. So I end up getting negative 21. So f of 1 comma 3 is just negative 21. But notice if I ask you to find this, I'm asking for something different entirely. So what if I asked you to find f with a subscript of x of 1, 3? Okay, well this means partial derivative with respect to x. So I'm not going to plug these numbers into the original. I need to find the partial derivative with respect to x. So before I can do the plug-in step, I need to do that. Okay, I need to find f, the partial derivative of f with respect to x. So here's the strategy I really want you to try to use. Okay, so by the way, that means what is being treated as a constant? Okay, we're going to treat y as a constant. If you will use this strategy, it will make this easier. So let's go back up top. Okay, what is going to be the constants then? 5 and y both, right? They're both constants. So I'm just going to pull down those constants, and then I can just do the derivative of the x part normally. Okay, so that would be 3x squared. Okay, same thing here. I'm going to pull down anything that's a constant. So what would be the constant here? Notice it would be 4 and also y squared, because anything with y in it is just treated like a constant. So then I'm just going to do the derivative of just this piece. So I'm going to circle these. The only thing I'm really taking the derivative of is the circled pieces. Okay. Notice the derivative of x is just 1. So the equation is 15, x squared y, and then minus 4y squared. So I'm going to circle this. So now if I'm asked to plug 1, 3 into that, just like you would expect, okay, this is your x and this is your y, and then just plug it in. So it's going to be 15 times 1 squared times 3 minus 4 times 3 squared. So this will end up being 45 minus 4 times 9, which is 36, or 9. Okay. And like we did before, remember, this describes the rate of change of x if y remains constant. Okay, the rate of change would be 9. Okay, so let's look at one with maybe an e in it. So if I tell you that f of xy is 3x e to the y power, and I ask you to find f subscript y of 1, 0. Okay, so this means that I'm going to find the derivative with respect to y. And it means I want to treat x as a constant. Okay, so let's do that. So if I want the derivative with respect to y, then I'm going to treat x like a constant. That means pull the constant piece down. The only part I'm actually taking the derivative of is this piece. Okay, the other part's acting as a constant. Okay, so then what would be the derivative of e? It would just be itself. Okay, so that's kind of a strange one, right? But this is the answer. And so now if I want to find f of subscript y of 1, 0, it would be plug in 1 for x, plug in 0 for y. Okay, anything to the 0 power is 1, so that would end up giving me just 3. Okay, so that means this is the rate of change of y if x remains constant. Okay, so let's look at one more, and then we're going to look at some ways that we can apply this, okay, to more real-life scenarios. So let's say that f of xy was 2xy divided by 1 plus x squared y squared. And I told you I wanted you to find f subscript x of 1, negative 1. Okay, so this again means find the derivative with respect to x and treat y as a constant. Okay, but also notice that this is a quotient, so I am going to have to use the quotient rule. It's been a little while since we've had to use the quotient rule. Okay, so I'm going to remind you in words what it is, but you definitely need to look it up if you're shaky. So if I want the partial derivative with respect to x, I am going to do bottom, okay, times derivative of the top. So here's where you want to pause, right? Derivative of the top, remember it's with respect to x, okay? So if I pull down the constant portion, which is 2y, and then I just take just the derivative of the x part, Okay, so again, if you want to circle this and this, that is the only thing you're actually really taking the derivative of. So what's the derivative of x? Just 1. And then it's minus the top times the derivative of the bottom, but again, it's just with respect to x, so the derivative of 1 is just 0. Okay, then I'm going to pull down the constant portion, which is y squared, and now find the derivative of the circled portion, which would be 2x. And then that's all over the bottom squared. All right, so there's kind of a lot going on here, so we're going to see if we can clean it up just a bit. Okay, so we're going to do distributive property. So this is going to be 2y plus, because 2y times 1 is just 2y, and then 2y times this would be 2x squared y cubed. Okay, and then here you would multiply through here as well, but notice if you multiply that by 0, you're just going to get 0. So this would be minus 2 times 2 is 4, x times x is x squared, y times y squared is y cubed, and then over the bottom squared. But if you're paying attention, notice we have some like terms. Okay, these two guys are perfectly alike. It's x squared, y cubed. So just think of it like I have 2 of something and I'm going to take away 4 of them. So that's going to leave me 2 of them. And then over the bottom. So I'm going to go ahead and circle this. This is as far as I can take this. Notice, just like before, I don't mess with the bottom really. I don't simplify the bottom. I just try to simplify the top as much as I can. All right, so now let's look at plugging in the numbers they asked us to plug in. Okay, so everywhere there's an x, I'm going to replace it with a 1. Everywhere there's a y, I'm going to replace it with a negative 1. So you just want to be really careful. So it's 2 times y minus 2 times x squared times y cubed. And then on the bottom, it is parentheses 1 plus x squared times y squared, and then close the parentheses and the whole thing squared. So you can have your calculator do all of this, okay? But what you'll end up getting is 0 over 4, okay, which is just 0. Okay, so by the way, if the rate of change is 0, what does that mean? That means that it's not changing, right? So this is the rate of change of x when y remains constant. In other words, at that point, what it's telling you is that x is not changing, right? If the rate of change is 0, it means it's staying steady. Okay, so let's look at some word problems. The content's not going to be more challenging if you'll just remember that when I take a partial derivative, I treat the other one like a constant. So let's say that I have this equation that gives the miles per gallon, or the MPG, of a new car as a function of 2 variables, okay, as a function of the tire pressure, which we're going to call x, and the average speed you drive, which is y. Okay, so both of those things affect your MPG, okay, whether your tires are properly filled and definitely how fast you drive. So I want you to find each of the quantities and then briefly explain. When I say briefly explain, I just want you to explain kind of like I have been doing in red. Okay, just explain to me what it means, what the answer means. All right, so the first thing I want you to find is m of 32, 50. Now remember, x is tire pressure, y is speed. Okay, so notice I don't have a subscript here, right? So I'm not being asked to find a partial derivative. I'm actually just being asked to plug this in. Okay, so this is my x and this is my y, and I just need to plug it in. So, and this is going to give me my MPG. So it's 68 plus 0.3 times 32 minus 0.8 times 50. Okay, so you end up getting 37.6, I think. Let me punch that in again. I already did it before, but let me make sure. So 68 plus 0.3 times 32 minus 0.8 times 50. Yeah, so 37.6, okay? So make sure that you understand what kind of answer this is, okay? What this is telling you is that the MPG of the car is 37.6. They're getting 37 miles per gallon, okay? When the tire pressure is 32. By the way, the measurement for tire pressure is PSI, okay? And speed is 50 miles per hour. Okay, so up here, let's go ahead and mention that tire pressure is in PSI. Okay, so what if I instead asked you for M sub x of 32 comma 50? So that means I need to take the derivative with respect to x, right? That means I need to treat y as a constant. So before I can plug that in, let's figure out what the actual equation would be. Just go a piece at a time, okay? So what would the derivative of 68 be? Well, that's just a constant. The derivative of that is 0, okay? What's the derivative of 0.3x? Well, the derivative is with respect to x. That means treat that as you normally would. So normally the derivative would be 0.3. But then we're supposed to treat y as a constant, right? So that means the derivative of a constant by itself without anything attached to it is just 0. So we get 0.3. Okay, so what this means, remember x is the tire pressure, right? So it means that the tire pressure let's write it down here. It means that the MPG, sorry about that, the MPG increases by 0.3 miles per gallon when the tire pressure changes. Okay, so the MPG increases by 0.3 miles per gallon when the tire pressure changes by 1. Okay, it's understood to be a 1 there. Okay, and speed remains constant. Okay, so the overall equation is changing by 0.3 when the tire pressure changes, but the speed remains constant. Okay, because remember we treated y as a constant. Okay, so let's look at another one. So let's say a company makes 2 types of calculators. And sells X and Y quantities of them respectively. So one of the calculators we sell X number, the other calculator we sell Y number of them. And let's say that the revenue for the company, since they sell 2 items, the revenue is R of XY, and it's 80X plus 90Y plus 0.04XY minus 0.05X squared minus 0.05Y squared. I know I kind of squeezed that in. And let's say that the cost is C of xy equals 8x plus 6y plus 20,000. So let's say I asked you to find the profit with a subscript of x of 1200, 1800. And also the profit with subscript y of the same numbers. And explain. All right, so first of all, I'm talking about profit, but I'm only given revenue and cost. So profit is always revenue minus cost. I know this is a new form of profit, revenue, and cost, but it just means there's two variables. So make sure we keep this straight, right? The revenue was that long one, so I'm going to write it kind of smaller. 80x plus 90y plus 0.04xy minus 0.05x squared minus 0.05y squared. And I want to subtract off the cost, which was 8x plus 6y plus 20 grand. It's important that you include those parentheses. Okay, because that's going to change what you get. In other words, this minus sign is definitely going to distribute to all of this. Okay, so I'll let you kind of work that out, but notice 80 minus 8 is going to be 72, so this is going to be 72x. And then I'm going to have 90 minus 6, so that's going to be 84y. The rest of the variables look like they're just going to stay the same because they don't have anything to combine with. But then don't forget to subtract your 20 grand at the end. In other words, it's minus 20,000 now because of that negative sign distributing. Okay, so first, let's figure out the derivative with respect to x. Okay, so we're just going to go through this slowly, one term at a time. Okay, remember, x parts get treated as normal, y parts get treated as constants, okay, for the derivative with respect to x. So the derivative of 72x is 72, okay? But the derivative of 84y, that is a complete constant completely by itself. The derivative of a constant is always 0. Okay, for the next one, let's pull down the constant pieces, right? That's always what we do with constants, with derivatives and antiderivatives, right? We just pull them down. And then find the derivative of the x part, right, which is just 1. So that's times 1. What about here? I can treat this derivative completely as normal. Okay, so if I move the power out to the front, this is going to be 0.1x. Okay, what about both of these? Okay, this is a constant for sure. This is treated as a constant. So notice I'm just going to get 0 for the derivative for each of them. So if I clean this up, I'm going to get 72 plus 0.04y minus 0.1x. Okay, and that is going to be my equation for the derivative with respect to x. So let's plug in the numbers they asked, and then we'll do the other direction, the derivative with respect to y. So now let's find the derivative with respect to x after we plug in 1200 and 1800. So it's going to be 72 plus 0.04 times 1800 minus 0.1 times 1200. Okay, plug 1200 in for x, plug 1800 in for y. And if you do that, you're going to get $24. Okay, so what this means is that the profit, the rate of change for the profit is 24, which means the profit is increasing. If it were negative, it would be decreasing. So the profit will increase by $24 for each type of the first calculator that's made. okay, while the number of the second calculator stays constant. Okay. So let's find the derivative with respect to y now. So I'm back here, okay, where I'm pointing. So remember, now I'm treating x's as constants. So if I take the derivative of just a flat constant, it's 0. The derivative of 84y is treated as normally because now it's the derivative with respect to y. Okay, so here I'm pointing here. So what do I do with any constant part? Remember, 0.04 is a constant, but so is x. So I'm just going to pull that whole thing down. And then the derivative of y is just 1. Okay, what about here? The derivative of this, that is full constant, right? The derivative of a constant is just 0. And then the derivative of this, I would move this to the front, so it's going to be negative 0.1 y. Because remember, the y's are getting treated as normally now. And then the derivative of the constant is still 0 there. So the rate of change equation, if we're changing y rather than x, is 84. I think I just lost something. Oh, I forgot to write my x here, right? Sorry about that. All right, so let's go back there just so you know where I got that. Remember here, I mentioned that I needed to pull all that down as a constant. I just forgot to write the x. So when you take the derivative, you pull down both parts of the constant, and then you evaluate the y derivative as normal. So this would be 0.04x minus 0.1y. Okay, so now let's plug in the same 1200 and 1800. 1200 for x and 1800 for y. Okay, notice if you do that, you get a negative number, which is never pleasant when we're talking about money. Okay, so what that means is that the profit will decrease by $48 for each type of the second calculator that's made if we keep the number of the first calculator constant. So if the business owner had limited resources, he should definitely put all of his resources into making the first calculator at this stage in the game, right? Because the second calculator is really not profitable for him right now. Okay, and that is a lot of the application basis for partial derivatives. It's the fact that, you know, companies have limited resources. So when they're trying to decide, should I change this quantity or should I change that quantity, it's helpful to do a rate of change based on the individual changes for both things, okay, and then see which one gives you a better return. Okay, so another application is we can look at the partial derivatives and tell whether or not we have competitive products versus complementary products. We're going to talk about complementary products in a minute. So I think competitive products, we know what those are, right? Those are products that are often substituted for each other. So the demand increase, if you are true competitors, when you have an increase in demand for one, so demand increase for one causes demand decrease for the other. In other words, they're kind of substitutes for each other. Okay, so an example might be real whipping cream and imitation whipping cream like Cool Whip. Okay, typically people will buy one product or the other, right? They won't buy both products. Okay, there's exceptions, but those would be considered competitive products. Okay, butter and margarine would be considered competitive products. You usually buy one and not the other. But complementary products are just kind of what they sound like. They complement each other. Okay, so these would be products that are often bought together. So it's not true that buying one means that you usually won't buy the other one. They're usually like a package deal. So here, the demand increases / decreases for both products. Okay, so an example might be like fishing boats and outboard motors. Okay, these aren't competitive products. In fact, these are products that complement each other, right? So the sales of them, the trend for the sales of them tend to go up together, okay? Or maybe things like peanut butter and jelly, right? Those two items complement each other, and often those are bought together. All right, so let's say that I tell you that X is F of P and Q, okay? And this is going to represent the demand for product A. And Y is going to be a different function of the same letters. And that's going to represent the demand for product B. Okay, so notice the functions are different, but the letters being used are the same. Okay, in this case, P and Q. All right, so some things are true. I am not going to make you memorize these facts, but you will have to know how to find partial derivatives. So here's how this works with economics. All right, so the first scenario is that the derivative with respect to Q of your first equation is greater than 0. And the derivative with respect to P of your second equation is also greater than 0. Okay, so I'm going to say both of these things are true. In other words, both of these are positive. Okay, then what that means if they're both positive is that products A and B are competitive. I spelled competitive wrong. Competitive. There we go. In other words, they're substitutes for each other. Okay, if you can show that the partial derivative with respect to Q of the first equation is less than 0, and the same is true of the second equation, but with respect to P. Okay, in other words, if you can show that they're both negative, then they are complementary products. In other words, they are products that are traditionally bought together. So as the demand for one goes up, so does the other. As the demand for one goes down, usually so does the other. But the last two scenarios involve when you have different signs. So let's say that this one is greater than or equal to 0, and G, the derivative with respect to P of G, the G equation, is less than or equal to 0. Okay, so notice instead of being the same signs, they are different, or 0. Then we say they're neither. The products are neither competitive nor complementary. In other words, they don't really have a relationship to each other, and any relationship might be kind of random. And then lastly, the opposite. If this one's less than 0, but this one's greater than 0, okay, so notice still different signs, right? So it really doesn't matter which one's which. They either need to be the same sign. So if they're both positive, it's competitive. If they're both negative, it's complementary. If they switch signs between them, then they are said to be neither. Okay, it usually means the products are not related to each other whatsoever. So let's look at a couple of these. Now, I want you to use your common sense to kind of guess what you expect these to be ahead of time, and then we'll see if the math matches. Okay, so the demands for coffee brand A and coffee brand B are given by the following patterns. Okay, the demand for coffee brand A is the equation involving P and Q that looks like this. 200 minus 5P plus 4Q. And the demand for brand B is a different equation involving the same letters, and it looks like 300 plus 2P minus 4Q. Okay, so just to remind you, this is the demand for brand A, and this is the demand for brand B. Okay, now, if you use logic, right, would we expect two different coffee brands to be competitive or complementary or maybe neither? Okay, I would probably expect them to be competitive, right? Because if you buy one brand of coffee, you're probably not also going to buy another brand of coffee. You're going to substitute one for the other. Okay, but let's see if the math backs that up. So what we need to find is the derivative with respect to Q of the first equation. Okay, so I'm going to leave some space, and we need to find the derivative with respect to P of the second equation. Okay, notice if you look at our 4 cases above, that's always what I'm being asked to find. Okay, so let's start with the first one. I want to find the derivative with respect to Q. In other words, I'm going to treat P as a constant. Okay, so the derivative of 200 is a constant no matter what, right? That's just 0. Okay, the derivative of 5p, remember p is a constant, is also 0. But the derivative of 4q, I treat the q equation or the q part of the equation as normal. So the derivative is 4. So that's 4. Okay, notice it's positive. Now let's do the second equation's derivative with respect to p this time. Okay, that means we're going to treat y as a constant. Treat q as a constant. I forgot we switched letters. Don't let the p and q throw you off. We're just using p and q instead of x and y. That's because we usually use price for demand equations. Okay, and then they're using q as like a secondary price. Okay. Or the price of product B. All right, so if we treat Q as a constant, let's go back up here, and we're looking at the second equation, remember. So the derivative of 300 is 0. We're treating P as normal, so the derivative of 2P is just 2. And the derivative of this whole constant is 0. So I end up getting 2. Okay. Notice that this is positive and so is this. So because I got positive results for both, okay, it means that these products are competitive. That's what we would have expected, right? So what that means is if you buy coffee brand A, you are probably not very likely to buy coffee brand B because you are using it as a substitute. Okay, so let's look at one more. And just know you're not going to have to memorize any of those cases. The main thing you need to learn from this lesson is how to find a partial derivative. Okay, and it's always treat one variable normally and treat the other one like a constant. So if you're a little shaky on this, you might need to rewind the video, watch some of the examples multiple times. Okay, watch how I treat and how I bring down the constant terms first and then take the derivative. That's probably the best strategy. So let's say that I want to find the demand, or I'm given the demand equations for tennis rackets and tennis balls. So let's say that this is the equation for the demand for tennis rackets, and this is the equation using the same variables for tennis balls. So this is tennis rackets, and this is tennis balls. Now if you're using common sense, okay, what would we expect about tennis rackets and tennis balls? They're not competitive, right? You're not going to buy one versus the other, but you very likely might buy them together, right? Which means they might be complementary, okay? But we're not sure, okay? So we're going to show it with the math. So again, I need to find two things: the derivative of the first equation with respect to Q, and I need to find the derivative of the second equation with respect to P. Sometimes my Q's end up looking like A's, so I'm trying to fix that. Okay, so in this one, again, we're going to treat P as a constant. Okay, so pay attention to kind of how I do that. So we're only looking at the first equation. So the derivative of 500 is 0. The derivative of this term is treated as normally because it's a P term. So it's going to be negative 0.5. And then the derivative of this, well, that's just a full constant, right? So the derivative of that would just be 0. Oh, sorry. No, we're with respect to Q. Sorry about that. So find the derivative. So I did that backwards, right? I treated P as a constant, so don't do what I just did. But sometimes you just lose your train of thought in the middle, and that's what I did. So I was doing it backwards, right? I was treating Q as the constant. Okay, I'm supposed to be treating P as the constant. So the derivative of 500 is certainly 0. But the derivative of this is full constant, right? So that would actually be 0. And then treat this normally. What would be the derivative of Q squared? It would be minus 2Q. Okay, so notice I don't get a number here, but 2Q would definitely be negative because remember Q represents the quantity of, in this case, tennis balls. Okay, tennis rackets is P, tennis balls is Q. Okay, so that is still negative. So now let's do the derivative with respect to P. So of course I'm going to treat Q as a constant. Okay, and I'll keep it straight this time. So we look at second equation and we treat Q as a constant. So second equation, derivative of 10,000, that's just a constant, derivative is 0. The derivative of 8P is treated as normal, so it's going to be minus 8. And then the derivative of this guy, Q is a constant. And notice it doesn't have anything else with it, so that would just be 0. So here I get negative 8. So notice both values are actually negative. Okay, so that means that they are complementary. Okay, so on my math lab for this section, it's going to ask you, like we did here, it's going to ask you for each of those partial derivatives, and then in the end it's going to say, okay, what's your conclusion? Are they competitive? Are they complementary? Or are they neither? Okay, they're complementary if they're both positive. They're competitive if they're both positive. They are complementary if they're both negative, and if one is positive and one is negative, then they are neither. Okay, it just means that they don't really have a strong relationship to each other one way or the other.